Bonding, that's going to be the topic of this lesson and really the central theme of the entire chapter here. So in this lesson, we're going to go through the three major types of bonding here: ionic, covalent, and metallic. And we'll talk about the different compounds and substances that have these different types of bonding and some of the properties of those. And really setting a good foundation, because in the future here, we're going to get more into drawing out structures. So we'll call them Lewis dot structures, and then the molecular geometries, the shapes that different molecules take and things of this sort. This lesson's part of my high school chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss a lesson, subscribe to the channel, click the bell notification. You'll be notified every time I post a new lesson. All right, so three different types of bonding here, and we're going to talk about what is the key characteristic of bonding and how do you predict when each of these exist. And you guys kind of already got a window into this. So earlier we talked about naming different types of compounds. We already talked about naming ionic and molecular compounds, and we had to learn how to identify those different types of compounds from the get-go. So, but in ionic compounds, we really look at this as involving a transfer of electrons, whereas covalent bonding, we look at this as involving a sharing of electrons. We'll get to metallic in just a little bit. So we're going to spend far more time talking about ionic and covalent. We'll spend just a little bit of time talking about metallic and probably won't talk about it again in the entire course. Just an FYI. So not something as commonly presented in the curriculum here. So all right, so ionic compounds, you guys learned how to recognize those back in the day, and you learned to recognize them as involving a metal, something from the left-hand side of the periodic table, as well as a non-metal, something right up in the upper right-hand half of the periodic table. And so that's not going to change here. So ionic compounds are going to be a metal with a non-metal. And the idea is you're going to have to use an element that has a low ionization energy that can easily lose an electron. And that's based on the trends we learned in the last chapter. That's going to be the metals. They have low ionization energies. And then on the non-metal side, you're going to want to have something with a very negative electron affinity if possible. That way it releases a lot of energy when it gains the electrons, and that's your transfer of electrons. The metal loses, the non-metal gains, and hopefully it's energetically favorable. Well, we actually use another metric besides ionization energy and electron affinity that we learn in this chapter called electronegativity. And so it turns out electronegativity, the most common scale is called the Pauling scale. It's on your handout there. I'll put it up on the screen here. And what you can see is that fluorine has got the highest value at 4.0 on the Pauling scale, the most electronegative element. And generally, as you go up the diagonal closer to fluorine, you get more electronegative. So elements get more electronegative as they go up and as they go left to right across the periodic table. So fluorine's the most electronegative, oxygen is second, nitrogen and chlorine duke it out for third, and depending on who you talk to will affect who's in third place. But generally, you should know that fluorine's first, oxygen second, and then after that, just the closer you get to fluorine, the more electronegative. Well, the idea is that if you have a big enough difference in electronegativity, we'll call it an ionic bond. But if it's less than a certain value, we'll call it covalent instead. And so for ionic, that difference in electronegativity that I'll call delta EL here, it's got to be greater than 1.7. And so that is actually the true definition of when you actually have an ionic bond. So, but we're never, we're not going to just give you this Pauling scale every time you need it and stuff, or expect you to memorize it or anything like that. So rather than actually having you figure out this technical definition, we usually just suffice it to say that metal and a non-metal, that's what typically happens, so great. Well, it turns out there are examples of actually having a metal and a non-metal that actually properly would be defined as a covalent bond. So, but these are the exception, not the rule, and it's not something we'll ever expect of you in a high school class or even in a college general chemistry class, something in a much more advanced class that we'd even talk about. So, but I just want to cover my bases, make sure I'm not telling you, any explicit lies here. So, but generally this is where this idea of metal and non-metal comes from. They're going to have an electronegativity difference greater than 1.7. Whereas for covalent bonding here, we're going to have an electronegativity difference less than 1.7. And again, that's generally going to happen when you have two non-metals. And that's why we recognize covalent bonding occurring between two non-metals, whether it be two of the same or two different, but it's two non-metals, that's what we'll kind of go with. So I give you these very technical definitions and introduce electronegativity to you, but the truth is, again, you're not going to have to memorize a table of electronegativities. You're probably not always going to have this table in front of you. And so suffice it to say, we oversimplify this and we just say metal and non-metal, ionic. Two non-metals, covalent. Life is good. Well, what about metallic over here? So metallic, rather than simply a transfer of electrons or a sharing of electrons, it does involve a sharing of electrons, but not in the same way as covalent bonding. And oftentimes we explain the model by saying it's a sea of electrons, a sea of electrons. And so the way it works in a metal, so like say you just got like pure copper metal or something like that. You got all these lovely copper atoms. So, and it turns out the valence electrons are not really belonging to any individual copper atom. They're loosely held by all of them. And as a result of these loosely held sea of electrons, that is actually what makes metallic elements and alloys and stuff like this. I almost said metallic compound. There's no such thing as a metallic compound. So, but these different metals and their alloys and stuff like that, which are combinations of metals, that's what makes them electrically conductive. They have this loosely held sea of electrons. So it turns out electricity is the flow of electrons. And if you're already full of loosely held electrons, that's going to make electron flow through you as a material much easier, much more likely to happen. So that's what actually makes metals electroconductive. It's this sea of electron model. So for ionic, it's a transfer of electrons. For covalent bonding, sharing of electrons. For metallic, this sea of electron models where the valence electrons are loosely held. Okay, so now let's talk about the different types of substances that result. So, and in this case, it turns out if you've got ionic bonding, then you are an ionic substance, an ionic compound in this case. And so, good example would be something like NaCl, but we shouldn't forget about our polyatomic ions. You can throw a polyatomic ion in there like NaNO3, that would be one. So, but the trickiest ones are the ones that involve ammonium. So ammonium is NH4, and if I put like NH4Cl or something like that, this gets tricky because these are all nonmetals, but it is still an ionic compound because it's with a polyatomic ion. The NH4 plus is the cation, and the Cl minus is the anion. You still have a cation anion, that's still an ionic compound. So if I want to ask you which of the following is an ionic compound and give you a really tricky example, I'm going to give you some sort of ammonium compound because it's all nonmetals but is still ionic. So make a mental note of that. All right, so turns out covalent compounds, on the other hand, turns out there's two types. We can't just say covalent compound because they really fall into one of two categories. And that first category is going to be molecular, and that is the vast majority. But the other one is going to be what we call a network covalent solid. And these are not very common at all. The vast majority of compounds made of only nonmetals are going to fall into this molecular category. So couple oddballs with this network covalent, we'll cover them very briefly, but diamond is a popular one made of pure carbon. So, and then quartz, which is SiO2, silicon dioxide there, also an example. And so it turns out that these guys don't actually form individual molecules. They form big crystalline structures. Turns out that is also true about ionic compounds. They just form big crystals. So if you got like sodium chloride, it doesn't just have one sodium and one chlorine. The bigger the crystal, the more sodium ions and chloride ions it has. So same thing with diamond. So the bigger the diamond, the more carbon atoms. So both of these are crystalline solid. They form big crystals. We say they have a lattice associated with those crystals and stuff like that. Whereas molecular compounds, these are the ones that form individual molecules. So something like, say, water or carbon dioxide or things of this sort. So how many hydrogen atoms are in a water molecule? 2. How many oxygens? 1. How many carbons are in a diamond? Well, I don't know. It depends on the size of the diamond because it's a big crystal structure. So that's kind of your difference here. So these are your molecular compounds. And again, if you've got a combination of nonmetals, if it's not one of the exceptions over here, and it's not one of these network covalent solids, and again, there's more than just these two, but these are the only two you're ever likely to see. So then it's going to be a molecular compound like water or carbon dioxide. Now, finally, we got metallic bonding, and that's going to show up in metallic substances. I can't really say compounds. So metals don't, when you have just metals, you either have a pure metal and it's just a pure element, so not a compound, or if you actually combine metals, it turns out they don't combine in these whole number ratios typically the way our ionic and molecular compounds do. So we don't really call them compounds. So, but you can mix metals together and you make alloys, and that's the name they go with there. So we'll call these metallic substances over here, whether it be a pure metal or a combination of metals that's an alloy. So, and if you look at kind of the difference in properties for these 4 different types of compounds. So some things you should know. So for ionic compounds, these are on your study guide there. So your ionic compounds, first off, they have super high melting points and boiling points. And the reason they do is to melt them or boil them, you actually have to break ionic bonds, which are pretty strong. So same thing is true with the network covalent ones. Again, with also forming a crystal structure, if you want to melt or boil them and break that crystal structure up, you actually have to break now covalent bonds, which also are really strong. And so for your ionic and your network covalent, they have rather high melting and boiling points, first thing to know. Now for your ionic compounds, they also are pretty brittle. So if you take a look at a typical ionic compound, let's make a little room here. So you get this nice 3-dimensional crystalline structure, so of alternating charges here. So plus, minus, minus, plus, minus, plus, plus, minus, plus, minus. And this expands out in 3 dimensions. The bigger the crystal, the more it expands out. But what you notice, though, is that for every cation, its immediate adjacent neighbors are all anions. That's what holds the crystal together. It's this plus-minus attraction going on here. Well, it turns out that what makes an ionic compound brittle is that when you put a stress on it, what you actually do is shift the layers. And if I shift this layer ever so slightly, this plus might be in this position now and be surrounded by all other plus charges. And so instead of attraction, you get repulsion, and crystals tend to fracture right along nice clean lines as a result of this kind of thing. So take, for instance, like say salt. So when I say salt, I mean sodium chloride in this example. So however, you're going to find out that in chemistry, we use the word salt in very generically, and it means any ionic compound is a salt. Now, the most likely ionic compound in your kitchen is table salt, sodium chloride. But technically from here on out, salt in a chemistry context is any ionic compound. So, but I'm going to talk about table salt, sodium chloride, for a second. So if you take a big salt lick like they put out for horses or for deer or something like this, so these big, huge blocks of salt, if you hit it with a sledgehammer, it's going to shatter into a million pieces because ionic compounds are brittle. And what's going on in this case is, again, when your sledgehammer contacts that big salt block, the layers shift. And so instead of attraction like we'd normally get, shift this over one position, and all of a sudden you get repulsion. And that's what's going on. Notice that would not happen with, say, a metallic compound. If you hit a big iron anvil with a sledgehammer, it's not going to shatter into a million pieces because metals are not brittle. This brittle property is unique to the ionic compounds up here on the list. All right, so molecular compounds. So molecular compounds have significantly lower melting and boiling points than either the ionic compounds or the network covalent compounds. So significantly lower. And the idea is that you're not actually breaking any bonds when you actually melt or boil a substance. So what you're actually doing is breaking something much weaker, this weak attractive force between the molecules. It's not a bond. It's much, much weaker. We call them intermolecular forces. We'll go into them further in a couple chapters. So, but these intermolecular forces are much weaker than actual ionic or covalent bonds. And so to melt or boil these molecular substances takes way less energy, and they occur at way lower temperatures. So to kind of give you a comparison's sake, so if you want to melt, say, ice, water, it happens at 0 degrees Celsius. If you want to melt sodium chloride, it's like 800 degrees Celsius. If you want to melt a diamond, it's in the thousands of degrees Celsius. So big differences, again, molecular, far lower melting points than the rest of these. Cool, and that's all I really want to say about molecular compounds as far as their properties, those lower melting points and boiling points. Moving on to metallic properties, there are some unique properties you need to know about metals, and we're really not going to talk about metals again for the rest of the course. So there's 5 lovely properties you want to talk about, and one is that they're electrically conductive. One we already mentioned there. So they're also good conductors of heat, so they're thermally conductive, we might say, and that's why, if you touch a piece of metal that's on the stove, it gets hot in a hurry, right? So when it's been heating up on your stove, where there are other things like, a piece of wood, at least that's not on fire, that might not transmit heat as well, things of that sort, not as good of a conductor, but metals tend to be really good conductors of both electricity and heat. So, but there's also 3 new terms that you're probably, good chance you haven't seen before, that we're going to bring up in this context, and the first is luster. So luster is just the fact that metals are shiny. That's what it means to have luster. And indeed, metals tend to be shiny, so no big deal there. The next is that metals are malleable. So, and malleable here simply means that they can be pounded into different shapes, like pounded into sheets, and that's a property of metals. And then finally, ductile. Another word you might not be familiar with, and this just means that metals can be drawn into wires. That's what ductile actually means. And so these 3 properties right here are unique to the metallic compounds, and 3 you should file away, along with being both electrically conductive and thermally conductive. All right, so now we've kind of done an overview of the 3 different types of bonding and the different types of compounds or substances that result from them. We want to focus a little more on ionic and molecular, the 2 most common types. All right, so for ionic compounds, we've got one last thing to talk about, and we call this lattice energy. And lattice energy has a very formal definition. It is the energy it takes to pull an ionic compound apart into its gaseous ion. So, for example, here, if we did this for sodium chloride, we'd have solid sodium chloride, and we pull apart those ions, But not just any ions. The ions have to be in the gaseous phase. If you recall, we had definitions for ionization energy and electron affinity of also involving gaseous phase things, and same thing here with lattice energy. So this is the technical definition. You should be able to, if I give you any ionic compound, to write kind of a reaction out that is basically what defines the lattice energy. Now, it turns out you might be on the hook for comparing lattice energies among different compounds. And what really is going on here, if you have to pull apart the ions, then the lattice energy is really just a measure of how strong the ionic bonds are. And the stronger the ionic bonds, the higher the lattice energy. So what makes ionic bonds stronger and weaker? Well, two things. And the most important thing are the charges on the ions. So the greater the magnitude of the charges, where cations are more positive versus anions being more negative, is going to lead to greater attraction and stronger ionic bonds and a higher lattice energy. So we actually want higher charges if we're trying to pick compounds that have higher lattice energies. So again, +2 ions experience greater attraction than +1 ions. -2 ions experience greater attraction than -1 ions. And this is usually the most important thing. So this first example, we're going to compare these two compounds and their lattice energies, and kind of question you might get on a test, and you just got to figure out which one has a higher lattice energy. Well, the first thing you should do is assign charges to the cations and anions. So sodium and fluoride, sodium being a group 1 metal, as an ion is going to be +1, fluoride 1 electron short of having a filled octet is going to be -1. So, and then we go to magnesium oxide. So magnesium over here is an alkaline earth metal, so it wants to lose 2 electrons to look like a noble gas, or so we say. So, and then oxygen tends to gain 2 electrons to look like a noble gas, and so we've got +2 and -2. And so in this case, based on charge alone, it's easy to determine that magnesium oxide is going to have the higher lattice energy. So stronger ionic bonds, greater attraction between the ions since they have a greater magnitude of charge. That is the deal there. Now we also have a second comparison here. So, and that is based on size. Typically, this is only something we involve if the charges are all the same. And if they are, then we'll go to size. So, and the way size works here, is it turns out that shorter bonds are stronger bonds. And so shorter ionic bonds would be stronger ionic bonds, which means a higher lattice energy. So think about having a shorter stick and a longer stick. Which one's harder to break? The short stick is going to be harder to snap in half. So same kind of thing here, if you will. I'm just kind of pulling an analogous example there. So if we look at these two here, so MgO and CaS, so magnesium, again, +2, oxygen, -2, like we just figured out, but calcium's also +2, and sulfur is also -2 as well. And so here we've got exactly the same charges. And when you have that, well, then you have to default to your size. And so the smaller ions have a shorter ionic bond, and a shorter ionic bond, again, is a stronger one. And so in this case, magnesium 2+ is smaller than calcium 2+, and oxygen 2- is smaller than sulfur 2-. And as a result, magnesium oxide in this pair is also going to have the higher lattice energy. And these are typically the two kind of comparisons you get. It's either about a difference in charge, which is the first thing you should look for, or if the charges are exactly the same on all the cations and anions, then it's going to be a difference in size, and the smaller ones will have the higher lattice energy. So now we've got one last thing to discuss in terms of covalent bonding. So it turns out there's actually 2 categories of covalent bonds. We call one nonpolar and the other polar. So, and nonpolar, also referred to as pure covalent bonds or something like this. And what's going on here, if you hear that word polar, most common context that word shows up in everyday life would be like a polar bear. So why do they call a polar bear polar? Well, it lives either at the North Pole or the South Pole. That's the idea. So, and in this case, where do we get this whole idea of a North Pole and a South Pole from? Well, it turns out the Earth has a magnetic field associated with it, and so you have a magnetic North Pole and a magnetic South Pole. And actually, it's reversed. Our geographic North Pole is actually the magnetic South Pole, but whatever. So, but you have a North Pole and a South Pole, and it's a magnetic dipole of the Earth. And when you have a dipole, you have 2 poles. And for magnets, that's a north and a south. But in this case, we're going to have an electric dipole, and it's not north and south here. It's going to be plus and minus. And so it turns out you get a polar bond, a polar covalent bond, when you have a large enough difference in electronegativity. Now, if you guys recall, we already said, so if we go to 0 difference electronegativity to 1.7 over here, so anything higher than 1.7 was going to be termed ionic. So, and anything between 0 and 1.7 for an electronegativity difference from that, again, that Pauling scale, was going to be termed covalent. Well, it turns out this gets broken up a little further. Right here, we'll have 0.5. So, and it turns out anything from 0.5 to 1.7 we'll call polar covalent, and anything less than 1.5 we'll call nonpolar or pure covalent. And so what's really going on here is that as you go further and further to the right, you're actually getting more and more ionic character, and they draw a line in the sand at 1.7 difference in electronegativity and just say, yeah, anything past that we'll call ionic. But the truth is, even these polar covalent bonds have what we call partial ionic character, and the closer they get to a difference of 1.7, the more partial ionic character they have. So let's take a look at this here. So how do we know when a bond is polar or nonpolar if we don't have a table of electronegativities in front of us? So, well, you might not is the truth. However, so we're going to oversimplify this for you as well. And so typically the way it works, if you want to recognize a nonpolar bond, it typically is going to involve two identical atoms. Like let's say you've got chlorine bonded to chlorine, or bromine bonded to bromine, or fluorine bonded to fluorine, oxygen bonded to oxygen, something along those lines. Or it turns out there's one bond involving two different atoms that we expect you to know is considered nonpolar, and that's carbon to hydrogen. If you look on your table of electronegativities, carbon's got a value of 2.5, hydrogen's got a value of 2.1, so the difference between them is only 0.4, and it would therefore lie in this category of nonpolar or pure covalent bonds. Obviously, if you have two identical atoms, well, then you're going to have no difference in electronegativity. It'd be exactly 0, and that's another way you show up as nonpolar. Cool. There are other examples of two different nonmetals that actually would fall in this category. We're just not going to expect you to know it. It's too difficult to demand that of you. So outside of carbon to hydrogen, typically if you have two different nonmetals, we're going to consider that bond polar and teach you to do the same. Is it always true? No, there are exceptions, but we're not going to require you to know any of those exceptions. All right, so these polar covalent bonds, let's take a look at some examples here. So let's say we have carbon bonded to fluorine. So carbon's got a electronegativity value on the Pauling scale of 2.5, fluorine's up at 4.0. That's a difference of 1.5. That's got a significant amount of partial ionic character being down here close to 1.7. So, but definitely falls in this range and being considered a polar covalent bond. Now, a thing you're supposed to know also is that the bigger the difference in electronegativity, the more polar the bond. So question you might get on a test is I might give you carbon fluorine, carbon chlorine, carbon bromine, and say which of these is the most polar bond. So we have degrees of polarity here as well. And so it turns out carbon's got the lowest electronegativity of these three. So at 2.5, fluorine's at 4.0, chlorine's close to 3.0, and bromine's somewhere actually not too far from 2.5, truth be told. But we can see that we get the biggest difference between carbon and fluorine in electronegativity, and it therefore would be the most polar bond out of these three. So bigger difference in electronegativity, more polar bond, something else we might test you on. Cool, but this was the big delineation we wanted to make here, because we're going to talk about polarity. These polar bonds actually play a role in properties of molecular compounds, as we'll see a little later on in this chapter. If you have found this lesson helpful, would you consider giving me a like and a share? A couple of the best things you can do to help promote the channel. If you are looking for the study guide that goes with this lesson, or if you are looking for practice quizzes and chapter tests and things of the sort, check out my premium course on chadsprep.com.